If you are a VLSI enthusiast, then you might have heard these words: ASIC and FPGA. ASIC stands for Application Specific Integrated Circuit, and FPGA is nothing but Field Programmable Gate Array. So in today's video, we are going to discuss ASIC versus FPGA design flow in detail. So before moving ahead, I'm assuming that you have already watched previous two videos of this playlist. So make sure guys, link is given in the description. It will help you to understand this video. So let's start with ASIC. An ASIC is a custom built microchip designed to perform one specific task very efficiently. So once it is designed and manufactured, it cannot be changed or reprogrammed. In simple terms, an ASIC is like a custom built car designed only for racing, that is fast, efficient, but not flexible. You can consider the Apple A17 Bionic chip in iPhones, which is designed only for iPhones, then Bitcoin mining ASICs designed only for cryptocurrency mining, then Snapdragon SoCs optimized for smartphones, then TPUs, that is tensor processing units by Google, used for AI and machine learning. However, FPGA, that is Field Programmable Gate Array, is a reconfigurable hardware chip that can be programmed and reprogrammed even after manufacturing. It contains configurable logical blocks like CLBs, interconnects, and IO blocks that can be configured using hardware code, that is HTL. So first, let's understand the ASIC design flow. So you can see here in this diagram how this design flow works. Here, this is the more detailed ASIC design flow. Each and every step is there. So let's understand one by one. Starting with the specification. So specification is related with the definition and blueprint. Before any design or coding starts, you must clearly define what your chip should do. So it includes functional requirements like what the chip will do, for example, perform image compression, handle Bluetooth communication, or manage power supply. Then your performance targets, it defines the speed, that is the clock frequency, throughput, latency, power consumption, and maximum area, that is chip size. Interface requirements define how your chip communicates with other components like SPI, I2C, UART, PCI, USBs. And then technology selection. So choose semiconductor process like 7 nanometer, 28 nanometer, or 65 nanometer, and the foundry, that is TSMC, Intel, Global Foundries. As an example, you can consider a camera control ASIC may specify that it supports up to 4K resolution at 60 fps, communicates with image sensors via I2C, then uses less than 500 milliwatt power, fabricated in 14 nanometer technologies. So this step is like writing a requirement document before building a house or a software product. Next step is RTL design. So this is the coding phase of hardware design, and the goal is to describe how data moves between registers and how logic operations happen using hardware description languages, that is either Verilog, VHDL, or System Verilog. You will design data paths like adders, multipliers, shifters, then control logic like finite state machine, pipelines for high speed operation, and memory interfaces like SRAM, ROM. Make sure to always write synthesizable code, and you can avoid any kind of delays, then use non-blocking assignments and follow coding guidelines for naming, indentation, and reset handling in order to make it synthesizable. And remember guys, RTL design defines what the circuit does, not how it will be built physically. The third step is functional simulation or verification. So before fabrication, you must test your RTL design to ensure it behaves correctly under all conditions. So for that, write test benches, that is the separate verification files that apply inputs and check outputs, then perform unit testing of modules and integration testing of the full chip. Then use assertions and convergence metrics to ensure all scenarios are tested. So different types of verifications are there, like directed testing. It tests specific cases manually. Then random testing, it generate random inputs to cover corner cases, and formal verification that mathematically prove correctness. UVM, that is universal verification methodology, is an industry standard method for large chips. And for this step you can use tools like Model Sim, QuestaSim, Synopsys VCS, or Cadence Xilium. The next step is synthesis. So now that your RTL code is correct, the synthesis tool converts it into a gate level netlist using logic gates available in a standard cell library. So what happens? RTL, that is logic gates and or NAND nor flip flops, etc. Then your timing constraints like maximum clock frequencies are applied. The tool optimizes the design for area, speed, and power. And the output will be gate level netlist, timing report, and area and power report. You can use Synopsys design compiler, Cadence Genus, and this step translates your HDL code in real hardware logic. Then DFT insertion will be there. So after synthesis, we make the design testable so that we can check each manufactured chip for defects. And common techniques are scan chains that allows reading and writing of internal flip-flops during testing. Then BIST, that is built-in self-test. So it automatically tests the memories or logic blocks. Then JTAG, it provides a standard interface for debugging and testing. Then ATPG, which is automatic test pattern generation, so it generates patterns to detect stuck at or delay faults. And this ensures every chip that comes out of the fab can be tested efficiently. This is the purpose of DFT. I hope you guys are getting the basic idea about this ASIC design flow. Before moving ahead, if you are watching my videos first time, then follow VLSI Point for more VLSI related content. You can watch the podcast playlist, or multiple course lectures are available. If you are still in doubt that how to start career in VLSI, then you guys can join one-to-one career guidance session with me. Here you can see 1000 plus students have already joined and see the feedback. So if you have any doubt, just register, book your slot, and clear all your doubts. Next step is floor planning. So now the physical design starts, deciding how the chip will look physically on silicon. So these tasks include defining the die size and core area, then placing large blocks, that is memories, PLLs, analog blocks, then planning power distribution networks, that is PDN, and clock tree routes, setting up IO pads and block boundaries. So you can use Cadence Innovus or Synopsys ICC2 for floor planning. It's like designing the map of a city, deciding whether building blocks will go before construction. Then comes placement. So here is the smaller standard cells from synthesis are placed inside the floor plan. So the objective is to minimize wire length and congestion, to ensure cells are placed near related cells for timing, to maintain power distribution uniformity. And here cells are placed but not yet connected. So just remember this point. Next step is clock tree synthesis, that is CTS. The clock signal must reach every flip-flop at the same time or with controlled delay. So CTS builds a balanced tree using buffers and inverters to distribute the clock evenly. The goal is to minimize clock skew, that is difference in clock arrival time, then to reduce the clock latency and control power consumptions. Think of the clock as a heartbeat. So it must reach every part of the body at the right time. In a very similar way, whenever we design any circuit, then clock must reach at the same time to all the components to work efficiently. After CTS, there will be routing. So once placement and CTS are done, we connect all cells using metal layers. So different types of routing are there, like signal routing, which connects logical signals, then power routing, which distributes power, that is VDD and VSS, then clock routing, which connects clock tree paths. And checks during routings are no short circuits or open wires, then follow design rules for minimum spacing, that is widths, And now the circuit becomes a fully connected physical layout, guys. After that, we will have physical verification. So before sending the layout for the fabrication, perform final checks to ensure it meets foundry requirements. And the major checks are DRC, that is design rule check, which ensures all geometries follow fabrication limits. Then LVS, that is layout versus schematic, so it ensures layout matches the logical design. Then antenna check, so it prevents charge buildup on long wires during the fabrication. And finally, the IR drop or EM check, which ensures power integrity and reliability. So you guys can use Mentor Calibre or Synopsys IC validator for this step. So this is like a pre-production inspection for your chip. Next step is static timing analysis, that is STA. So now we confirm that timing requirements are met for every path. And the checks are setup time, that is data arrives before the clock edge, then hold time, data remains stable after the clock edge. Critical paths like the longest delay between registers determines the maximum clock speed. So for STA you can use Synopsys prime time. And remember guys, there will be no simulation, purely mathematical analysis of delays during the STA. After STA, there will be power analysis. So for that, you need to estimate the power consumption of the final chip. And different power components are there, like dynamic power due to switching of transistors, then static power due to leakage currents, IR drop, that is the voltage drops due to resistance in power grid. And the output will be power reports and thermal maps. And this step ensures that your chip will not overheat or drain battery too quickly. So it's a very important step. Finally, we will have tape out. So this is the final delivery of your design to the foundry for manufacturing. And the deliverables will be GDS2 or OSS layout file, then the netlist and timing reports, test data and verification reports, and finally the sign-off document. So this is your go-to fabrication milestone. Once done, you can't modify the chip. And here comes the fabrication part. That is the manufacturing of the chip. So the foundry now builds your chip on silicon wafers using photolithography. And this step involves the oxidation, doping, etching, and metal deposition, then layer by layer chip construction. Wafers are cut into individual dies. So this is the most expensive step and takes several weeks. Finally, the post silicon validation and testing. So once the chip return from the foundry, then the task will be use ATE, that is automatic test equipment, to test each chip. Then measure the performance, timing and power, debug and fix issue using DFT structures, and package the working chips for sale. So this ensures your chip works exactly as designed in real hardware. So this is about ASIC design flow. So ASIC design is suitable for mass production, but there are certain requirements like high upfront investment. A huge investment is required, guys. Then the advanced EDA tools are required. Expert engineers should be there in digital design, verification, physical design, and DFT, and the timing analysis. Then the foundry access like TSMC, Samsung, Intel for chip manufacturing. And yes, this ASIC really have a long development cycle from months to a year. So use when you want to produce millions of chips and need best performance per watt, because ASIC design is very expensive and time taking, and once it will be fabricated you cannot change the functionality. However, FPGA requirements are little different. FPGAs are flexible, fast, and ideal for prototyping. However, ASICs are powerful, efficient, and ideal for mass production. For FPGA testing, you can use FPGA development board like Xilinx or Intel boards. Then you can do HDL coding, or either using Verilog or VHDL or System Verilog. Then you must have the design tools like Vivado or ModelSim to test your code on FPGA board. So basically the story is you can write the code for any of your circuit and you can test the working of that code on FPGA board. That is very affordable. Most of you have already seen that FPGA board in your college lab. So you can connect that FPGA board, dump your program and test the functionality. So now we will discuss the complete FPGA design flow. what all steps are involved. So you can see here the details, starting from specification till hardware validation and back to iteration if needed. FPGA design flow is similar to ASIC but simpler because the chip is already fabricated and you just have to configure it. So starting from the specification. So same as ASIC, FPGA specification defines system behavior, then interfaces, performance goals, and choose an FPGA family, that is Xilinx, Intel, or Lattice. So basically you have to define the functional specification, then the IO requirements, how it will perform, like the speed, latency, and power, and finally the family. After specification there will be RTL design. So write the logic using Verilog or VHDL. Design smaller reusable modules and keep the code parameterized so that you can easily make the small changes in parameters. Then you will have functional simulation. So simulate your RTL behavior using either Model Sim or Vivado simulator and check that outputs match expected results for all test cases. So basically, first you write the code and then perform the simulation by giving different sets of input and then check the waveform whether it is coming correct or not. After simulation, here you can see the waveforms which you will get. Then there will be synthesis. So synthesis will convert your RTL into a netlist mapped to FPGA. So the resources will be LUTs, that is lookup table, then flip-flops, BRAMs, that is block RAMs, and DSP slices. And for this you can use the tool like Vivado or Quartus. After synthesis, we perform the implementation part. So as a synthesis, you can see here the diagram which you will get here. Here you can check all the blocks and all the input output signals to verify the functionality of your code. Then in implementation, first you have to translate, then map, place, and route. So translate means combine design and constraints. Map means map logic to available FPGA elements. Mean to say translate combines all the netlist and constraints into a unified logic design. And then there will be mapping. So it maps the logic available to FPGA resources like LUTs, flip-flops, BRAMs, or DSPs. Then there will be place and route. So place logic elements on physical FPGA location, and then during routing it will connect them through programmable interconnects. Here the FPGA tool automatically finds the best placement and routing. You need not to do it manually. Then there will be timing analysis. So it will ensure all signals meet setup and hold time requirements. So check for clock domain crossing and maximum frequency. So you can see here how the setup time and hold time is defined and where the input signal must be stable. After timing analysis, there will be bit stream generation. So it will generate the final file which is used to configure the code on FPGA. So this is basically the final output, that is .bit or .sof file that tells the FPGA how to configure itself. After bitstream generation, we need to program the FPGA. So what we do, we just connect that FPGA kit with your laptop or PC. Then you will load the bitstream into FPGA using JTAG or flash memory. You need to program that FPGA. And finally, there will be hardware testing and validation. So now you can test on real FPGA board and verify the output with LEDs, UART, or logic analyzers like chip scope or signal tap. So note one point here, guys. For simulation, we need design code and test bench. But for synthesis, we need your design code and XDC file where we define all the clocks and where you will check your output either on LEDs or using switches. Let me know in the comment box if you have ever used FPGA board in your college lab or for any of your project. Finally, there will be iterate and optimize. So this step is used to fix any bugs and to optimize for speed or power and regenerate the bit stream. Mean to say, if there will be any issue or bug, or if you are not getting correct output on FPGA board, then you can make changes in the code in the XDC file, and again you need to perform the simulation, synthesis and implementation. After that, do the bit stream generation, then connect your FPGA board, program it, and then again check the functionality. So this step is although fast and can be repeated as needed until you will get the right output. So now we will quickly see FPGA versus ASIC, basically a summary table. So FPGA is a reconfigurable hardware chip, however ASIC is a custom built silicon chip. The cost for FPGA is high per unit but no fabrication cost. So overall you can say the FPGA implementation is very cheap. However, in case of ASIC it is very expensive. In case of FPGA it is reprogrammable anytime, but for ASIC it is fixed after tape out. FPGA provides lower performance due to general architecture, however ASIC provide higher performance because it is custom optimized. In terms of power efficiency, FPGA is less efficient and ASIC is more efficient. Time requirement is very less in case of FPGA, but it is huge in case of ASIC. Similarly, some other differences are there which you can see here. Overall, I can say FPGA design is perfect for learning, prototyping and experimentation. However, ASIC design is the ultimate step where hardware design becomes real high performance silicon. So I hope now you guys have a better idea about ASIC and FPGA. And for testing purpose, if you are a student, if you are writing the code, making projects, then FPGA is fine for you because it's very difficult to do the ASIC implementation. But if your organization is connected with any fabrication unit, then you can easily do the ASIC implementation. So this is it guys. This is about today's video. We have seen in very much detail about ASIC and FPGA design flow. Still, if you have any doubt, then let me know in the comment box. And for one-to-one session, you can DM me on either LinkedIn or Instagram to book your slot. My request is to like this video if you really understood the concept. It gives me a motivation to provide more and more useful content to you guys. Share this video with at least 3 of your friends who are struggling to start career in VLSI. See you soon in the next video where we will talk about the fab labs, that is fabrication laboratories.